The reaction quotient Q is also something that can be helpful to chemists studying in equilibrium. And all reacting chemical systems have a reaction quotient Q. And Q can be a little weird because Q looks the same as an equilibrium constant K expression. So just like K, which is products over reactants, Q is products over reactants. And just like K, Q, you want to raise all products and reactants to their stoichiometries. So little c, little d, little a, little b, etc., etc. But why the reaction quotient is helpful to chemists is that if you have a known value of K, the known value of equilibrium, you can take a sample of your own chemical system and essentially calculate a type of Q, all right? It's products divided by reactants, same thing. If your Q, the measurement you take, is equal to K, then your system's at equilibrium and you're good to go. But what happens on a lot of reactions where you need a Q is that the reaction is slower, all right? And you're not sure if your system's at equilibrium or not. So if you measure your products and reactants to get a Q value and you find that Q and K are different numbers, then that means your system is not at equilibrium. So you can think about Q as a way to test if your chemical system has achieved equilibrium or not. A lot of times Q and K, no problem because the reaction is pretty fast getting to equilibrium. But if you have a reaction which is slower, then knowing Q and comparing it to a known value of K, by the way, will help you to see if your reaction's at equilibrium. To use Q, you must know what K is. All right, that's really the most effective way. If you're the first person to ever study this chemical reaction, then you just have to take a lot of reactions over long periods of time and see if the reactants and products, i.e. your value of Q or K, changes, all right? Once it's a pretty constant, then you can say you know K. But at first, if you don't know, you just got to do it. So the best way to use Q is if you have a known value of K, you do products divided by reactants to get a Q, and then you compare your Q to the known value of K to see if you're at equilibrium. Here's a reaction where, again, H2 and I2 are combining to make 2HI. And we talked about earlier how once the products and reactants are constant, that's when you're going to have the equilibrium. So earlier when I drew it, it was something like this right here. And everything to the right of that little weird thing I drew is equilibrium, but everything to the left is not equilibrium. Reactants and products are still stabilizing. So let's say you didn't know where you were in this graph, all right? You could be anywhere along the x-axis. If you were over here, then you wouldn't be at equilibrium. But if you'd allowed the reaction to progress to over here, then you would be at equilibrium. So this would be the time that you'd want to do a Q calculation. You would measure the HI and the H2 and I2 concentrations at that point along the x-axis, calculate Q, and compare your Q value to K. And again, Q is going to be HI squared divided by H2 and I2, same kind of form as K. Comparing Q and K, there's three possibilities. If Q and K are the same, if they're equal to each other, that means you're at equilibrium and you don't have to wait any longer. However, sometimes Q is less than K. This is, I think, the most common in these kind of scenarios. If Q is less than K, all right, then that means the reaction's going to shift to the products. You're going to make more product and more reactants will be used up. We're going to call this a shift to the right. If I say shift to the right, that means a shift to the products. And in a Q world, Q would be less than K. So again, what would happen here is if K, we'll say, was equal to 10, maybe your Q was 4, a number less than K. So that tells you then that you'd have this kind of situation and more reactants are going to shift to the products. Once in a while, if you're starting with product and shifting to reactants, and this happens once in a while, then and you calculate things, sometimes you'll have a Q that's greater than K. So if Q is greater than K, then that means that more products need to shift to reactants. This means the reaction is going to shift to the left. So Q less than K is fairly common if you're doing a Q calculation. It means you're not at equilibrium. Q equals K means you're at equilibrium. And once in a while, you'll have a Q which is greater than K. That means you're going to have more reactants, less products. If you need more reactants than products, then in the change part of the ICE table, the reactants will have a positive and the products will have a negative. But what's more common by far is the first condition where Q is less than K. That means your products are going to have more of them formed. In the change part, the products would have an increase and the reactants would have a decrease. And we'll see this here in a little bit. Also, if I say shift to the right, that's going to mean more products. Shift to the left means more reactants. And again, we all have to be talking about the same form of the same reaction for that to make sense. Here's a reaction again with N-butane going to isobutane. Here's the Lewis structures actually drawn out. You can see that N-butane is truly a butane, a butyl group with all hydrogens around it. Isobutane is a methyl propane. Isobutane's like the common name. But anyway, in this reaction, the equilibrium constant's been studied pretty well. The K value, 2.50. Now let's stop right there. 2.50 as a K is larger than 1. So once equilibrium establishes itself, you're going to have more product than reactant because K is a product-favored K. It's larger than 1. So at equilibrium, we would expect to have more isobutane than butane. And that's kind of a neat thing. You can start to see how this stuff all works out. So right away, from the value of K, you can tell if you're going to have more products or more reactants. This K is larger than 1. More products, we're going to have more isobutane than we have N-butane. So let's say that we have isobutane at 0.35 moles per liter and the N-butane, which I just abbreviate N right there, 0.15 molar, all right? Are we at equilibrium? Okay, if you stop right there, all right, at this first question, what we want to do here is we want to actually calculate our Q. All right, we're not sure if we're at equilibrium. We know what the equilibrium constant is, so calculating Q will tell us if we're at equilibrium or not. And more often than not, in these kind of problems, I guess you're not at equilibrium, we can use our Q and compare it to K to determine which way the reaction's going to shift. So let's see how this works. So first of all, Q, we need to calculate it. And Q has the same form as K. It's products over reactants, raise everything, etc., etc. So in this case, it's isobutane divided by N-butane, 0.35 divided by 0.15. It comes out to be 2.3. Q, 2.3, is less than K, 2.50. So that means that Q and K are not the same. We are not at equilibrium. And because Q is less than K, that means Q has to become a bigger number. Bigger numbers mean more product, less reactant. Q is going to shift towards K. We're going to see a shift to the right. Anytime Q is less than K, that means you're going to have a shift to the right. More isobutane is going to form and less N-butane will be there. So when equilibrium is established, the isobutane will go up from 0.35, and we could figure out what it is, but it'll go to a larger number. And the N-butane will go from 0.15 molar to a smaller number. It's going to decrease as as the products, the isobutane, increases. Here's a reaction. N-butane to isobutane, again at K at 2.5. We have an N-butane 0.020 and an isobutane 0.030. Is the reaction at equilibrium? Okay, so the first thing you got to do is figure out Q. Q is going to be isobutane divided by N-butane. And the concentrations we have, 0.030 divided by 0.020. So in the calculator, first first thing I would do is mathematically, if you don't want to do it in your head, 0.03 divided by 0.02. That's like 3 halves. K is going to be 1.5. And 1.5, our Q, is certainly not K. So we're not at equilibrium. So if Q is 1.5, 1.5 will become more like 2.5 given enough time. And to make 1.5 more like 2.5, we need to make the numerator bigger and the denominator smaller. So that means more isobutane, less N-butane. That means we're going to have more products than reactants when the shift occurs. But initially, we have too many reactants. So we need to turn some of them into products. Answer B here would be the right way. So again, here you can see mathematically, this is the value of Q. I just took products divided by reactants. Q and K are certainly not the same. Right now, we have too many reactants. We need to make more products. It's going to shift to the right side. Equilibrium concentration calculations are something that are going to be really helpful to us. And we're going to look at a little bit of math in this section, so I'm just letting you know. But let's look at a typical set of calculations, things you might run into in problems like these. So this reaction is our H2 plus I2 making HI, and the K value we saw earlier, 55.3. It's products divided by reactants. We're going to square the HI, but the H2 and the I2 are the same. So let's say that we decide to do this reaction, and we're putting 1 mole of H2 and 1 mole of I2, and we're putting them both into a liter flask. We can use this information to calculate the equilibrium concentrations of H2, I2, and HI. Before we do anything, though, the value of K will tell us if our answers are going to be right or not. So in this problem, K is larger than 1. That means product favored. So when we go through the calculations here in a little bit, at the end, we should end up with more HI than we have H2 and I2. H2 and I2, the concentrations will be going down, and the HI concentration will be increasing. At the end, though, H2 and I2 will not be 0. All right, they're going to be some small number, but they will go down as HI is made. And at the end, we should end up with more HI than we have H2 or I2. So to solve a problem like this, set up the ICE table once again. And remember, ICE tables will be reactants on the left, products on the right. ICE stands for initial change equilibrium. So for this reaction, here's what I have set up, H2 and I2, and then HI on the other side. Now remember that H2 and I2, the reactants, are going to have a different change sign than HI. And in this problem, as we talked about, the H2 and the I2 will be decreasing, and the HI will be increasing. And the other thing about the change line is that the stoichiometry for this reaction will be evident in the change line. So for this reaction, that's 1 H2 and 1 I2 making 2 HI. Change here will be affected by that, and we'll see that. Now, initially in this reaction, we have 1 mole per liter of H2 and 1 mole per liter of I2, and we don't have any HI. Now, H2 and I2 are going to go down by some amount, and let's call it X, okay? And X is how much not only the H2 decreases, but the I2 as well. H2 and I2 both have a stoichiometry of 1. On the other hand, as they go down by X, HI is going to go up by 2x. It's got a stoichiometry of 2 relative to the 1 H2 and the 1 I2. So at equilibrium, we're going to have 1 minus x for both H2 and I2 and 2x for HI. So x here is just the amount that these things are going to change. We're going to do a problem here in a little bit where we're going to solve for x. So remembering here that the Kc value for this equilibrium, 55.3, we can set this up. 55.3 is K, and that equals the equilibrium concentration of HI, which is 2x squared. Remember that we squared it. So notice that that stoichiometry of 2 popped in two ways. It's the change, that part right there, and it's also the order. That's kind of cool. And then in the denominator, we'll have the H2 and the I2, and both of them are 1 minus x. So it's like 1 minus x times 1 minus x. You can imagine we can abbreviate that as 1 minus x quantity squared, which is kind of cool. And believe it or not, at this point, one equation, one unknown, x. And if we can solve for x, we've got this. In the old days, i.e. when I took this class, basically, we did elaborate sets of algebra, all right, to figure out what x is. But I do want to point out that in this wonderful day and age of Google and all kinds of things, a lot of your calculators have a solve button on them. And man, oh man, I would have died for a solve button back in the day, okay? If you have a solve button on your TI or whatever kind of calculator you've got, I really recommend you get it out and figure out how it works, because man, the solve button is going to make just nothing out of most of these problems, which is really, really cool. So if you have a solve button, I highly recommend that you learn how to use it, because it's going to be very helpful to you in Chemistry 223. On the other hand, if you don't have a solve button, there's nothing wrong with doing this the old school way, and I'm going to show you some tricks how this works. It's not a big deal. All right, you can do it either way, but if you do have the solve button, oh man, check it out. But anyway, I'm going to assume at this point that you don't have the solve button, and that's totally cool. In this kind of problem, what I would do is I would take the square root of both sides, all right? Let me show that old equation one more time. Here it is again. Notice that it's like 2x quantity squared and 1 minus x quantity squared. So if I rewrite that, it would be 2x squared divided by 1 minus x squared equals 55.3. Well, in the old days, again, before the solve button, when I had to walk uphill both coming to and going from school, and etc. Anyway, what we would do is you can literally take the square root of both sides, all right? Square root of 55.3 is just a number. I don't know what it is. I'll tell you on the next page. But here's the cool part. 2x quantity squared becomes just 2x, and 1 minus x quantity squared becomes just 1 minus x when you take the square root. So the square root kind of cancels out the squared parts right there. So this part right here is what you get when you square root it. Square root of 55.3, 7.44. And square root 2x squared is 2x, and square root 1 minus x quantity squared is just 1 minus x. So this problem now is just good old algebra. We got to get the x's on one side. We got to get everything on the denominator. We'll multiply both sides by 1 minus x. If you do that, you get 7.44 times 1 minus x equals 2x. 1 minus x divided by 1 minus x cancels. Then you get all of the distributive property. So 7.44 times 1 is 7.44. And then the same thing times minus x minus 7.44x equals 2x. Again, get all the x's on one side, so that would be 9.44x equals 7.44. X will equal 7.44 divided by 9.44, 0.788. Again, making sure that's very clear. At this step, 7.44 equals 9.44x. You divide both sides by 9.44. These numbers cancel. You've got just x. And this part right here, you can see equals 0.788. So this is how I would recommend doing these problems. But again, if you have that solve button, you'll get really nice problems out of it. Anyway, that's the x value. That's what we were looking for. So back to the equilibrium parts of the ice table, the H2 and the I2 were both 1 minus x. So 1 minus 0.788, we get 0.21 moles per liter. And HI was equal to 2x. So 2 times 0.788, 1.58 moles per per liter. Now, these numbers might seem a little esoteric at first, like what do they mean, right? And I dig it. So one way to help you, remember, K's greater than 1, like 55.3, mean more products, HI, than reactants, H2 and I2. And lo and behold, you do have more HI. 1.58 is quite a bit larger than 0.21. That means you have more product than reactant. Oh, it's all coming together. So anyway, check this problem out. Taking the square root of both sides can be really helpful on some of these problems, just FYI, but also if you have that solve button, do it. Here's another problem. N2O4 can be made into NO2, all right? And N2O4 is diatomic, you can argue, like a type of diatomic molecule, two NO2s. But they do make a stable bond, and it ends up making NO2. N2O4 is mostly colorless, while NO2 has kind of a brown color. So it's kind of an interesting reaction. Just be careful with it. In this reaction, N2O4 going to NO2 has been studied. Notice the stoichiometry of 2, K 0.0059 at room temperature. Now this K is much less than 1, okay? And K's less than 1 mean more reactant than product. So at this equilibrium constant value, you would expect more N2O4, the reactant, than you would NO2. And that's kind of a cool thing. And there's the Kc expression. Again, products divided by reactants, square the NO2, but not the N2O4. Equilibrium constant, again, less than 1. So let's say that initially we have 0.50 molar N2O4. What are the equilibrium concentrations here? So in this K, which is less than 1, some of the N2O4 will make NO2. But because K is less than 1, we expect there to be more N2O4 at equilibrium than NO2. So to figure out what the actual numbers are, once again, let's set up that ice table. We'll have the reactants on the left and the products on the right. Initially, 0.50 mole per liter N2O4 and no NO2. Now, N2O4 has a stoichiometry of 1 and NO2 has a stoichiometry of 2. The N2O4 will be decreasing by x. The NO2 will be increasing by 2x, 2 to 1. So at equilibrium, 0.50 minus x, NO2 will be 2x. Remember, the equilibrium means you must have reactants and products. So you wouldn't put like 0 for NO2 and then minus 2x. That doesn't make any sense in chemistry. No negative mass. You have to have positive reactant and product concentrations for all equilibriums, at least in chemistry. But anyway, in this problem, then the equilibrium, 0.5 minus x for N2O4 and 2x for NO2. So we can set up now the equilibrium concentrations equal to the equilibrium constant. The equilibrium constant, 0.0059. NO2 squared would be 2x. That's the equilibrium NO2. And again, you square it again. You do it twice. And then for N2O4, 0.50 minus x. So again, we have one equation and one unknown x. 0.0059 equals 2x quantity squared divided by 0.50 minus x. Now again, this is a problem where if you have that solve button, score, you're good to go. However, if you're like me, who doesn't always feel, I feel kind of like still using the solve button is cheating, but I know that's old school and really silly. But anyway, if you want to do it the old school way, which is totally fine too, we need to rearrange this equation a little bit. So first we're going to get the 0.5 minus x out of the denominator. We're going to multiply both sides by 0.5 minus x. So then you have 0.0059 times 0.5 minus x, and 2x quantity squared becomes 4x squared. So you can see then in the second line there, 0.0059 times 0.5 is 0.0029, and then also 0.0059 times negative x, you can see that equals 4x squared, and you rearrange it to 4x squared plus 0.0059x minus 0.0029 equals 0. And if you remember from math classes, I've written it this way because this is the form you need for a quadratic equation. Now, in a quadratic equation, you always have an x squared, an x, and just a number. And the numbers in front, like here, this 4, that's the a, all right? And 0.0059, that's the b term. And c here is negative 0.0029. So c is negative 0.0029. So if you have a problem like this, write it as a quadratic. Ax squared plus bx plus c equals 0. And here c is a negative number. That's fine. A can be negative, b can be negative, whatever. But we use these a, b's, and c's in the quadratic equation. If you haven't used the quadratic equation for a while, it's quite all right. The quadratic equation, x equals negative b plus or minus square root b squared minus 4ac over 2a. And literally the b, a, and c numbers are those numbers we just pulled out of the equation. So knowing that, we can put all of those things in. So negative b would be minus 0.0059 plus or minus square root b squared 0.0059 squared minus 4ac, so minus 4 times a, 4, times c, negative 0.0029. Got to do a little bit of math here, all right, but no problem. We need to divide everything by 8, the 4 times 2, and when you do that, you get here negative 0.00074 plus or minus, there's the 1/8, the 1 divided by 8, and all that stuff in parentheses when you square root it, 0.046, or actually 0.046 is the number, and then you square root that. Sorry about that. Do the plus or minus part. Plus or minus literally means you'll either add it or subtract it. So 1/8 times the square root 0.046 is 0.027. That's the plus or minus part. X is going to have two values here. In a quadratic formula, you're going to end up with two values of x. And so in this case, the values of x, one will be negative 0.00074 plus 0.027, and the other one will be negative 0.00074 minus 0.027. Those are the two allowed values of x here. The good thing about chemistry is that negative values of concentration and mass, etc., are not allowed. So when you actually solve for x, you get a positive and a negative number. Positive 0.026 and negative 0.028. Negative x's don't fly in chemistry because that would imply a negative moles, a negative mass, and that's not how chemists roll. So in a quadratic formula, the negative value is always thrown out. Only the positive value is allowed because, again, mass is always positive. So in this problem, x is the positive 0.026. And in the initial equilibrium values, N2O4 was 0.50 minus x, so that would be in this case 0.47. Remember that you cut the significant figures off at the hundredth spot, so you did exclude the rest of it. On the other hand, NO2 was 2 times x, 2 times 0.026, positive 0.052. Now, remembering that the equilibrium constant was a number less than 1, we predicted there would be more reactant, more N2O4 than NO2. And that's what we're seeing, all right? 0.47 is a lot bigger than 0.052. So reactant favored Ks, more reactant. N2O4 is certainly greater than NO2. In quadratic formula, all right, if you have a positive and a negative value of x, like here, the positive number is the one you want. You don't want the negative one. Negative mass doesn't fly. Some of the examples we're going to see, you'll end up with two positive roots, two values that are positive. And if you see two positive values, you want the smaller x. The larger x, when you plug it back into the equilibrium, will end up with a negative number. So FYI on that one. So again, when you're doing quadratic, positive and negative, always pick the positive. If you do end up with two positive roots, then you want the smaller of the x values. The last thing we're going to look at in this section is what's called Le Chatelier's principle. And just like equilibrium is super important for the stuff we're going to talk about, Le Chatelier's principle has a lot of uses we're going to see. Le Chatelier was actually a person who was a miner. He was down like pulling minerals out of the earth and stuff. And he studied these systems and came up with this idea, which has a lot of impact in the things we're going to do. There's a lot of things that affect equilibrium. All right, we've already seen how you can add more like reactant quotients and stuff to see, but it's more than that. You can also have changes in temperature, changes of pressure. Lots of things will affect the equilibrium position. So Le Chatelier's principle is just how a chemical reaction will adjust to a change. Here's the actual wording. If a system at equilibrium is disturbed, the system tends to shift its equilibrium position to counter the effect of the disturbance. So it's basically a way to predict how a chemical system will adjust if more reactants are added or if the temperature is cooled, stuff like that. And it's a very powerful tool. We're going to see there's a lot of uses for Le Chatelier's principle, both in the lab and also outside of the lab. If you change the actual temperature of a reaction, you can use Le Chatelier's principle, but it's important to realize that temperature will affect the value of K, all right? So temperature effects are the first thing we're going to look at here for Le Chatelier's principle. And if you change the temperature, you are actually changing the value of K, making it more or less reactant or product favored, et cetera, et cetera. Let's say we have a soft drink, all right? And the soft drink has carbon dioxide in the water. The CO2 can become liberated as a gas. Well, this reaction, which has been studied a lot by soft drink and also beer producers and stuff like that, then the way that it's written, it's an exothermic reaction. If heat is a product, that means that it's an exothermic reaction. If heat was a reactant, we would say it's an endothermic reaction. And just as a quick recall from earlier chemistry classes, if heat is a product, if it's exothermic, the sign of delta H is negative. On the other hand, if heat was a reactant, it would be endothermic and the sign of delta H is positive. So anyway, knowing all of that, let's say that we're going to decrease the temperature. At first it might seem weird here, but how you can think about it is like you're pulling the heat out of the reaction by cooling it, all right? And you can literally think about this reaction as the reaction's getting cold. And if you go outside on a cold day and you're like, brr, you'll probably go back inside and get a coat or a shawl or something to make you warmer, all right? Well, the reaction's kind of the same thing. If the reaction is cooled, you can think about it like the reaction's getting colder. And it's going to try to make more heat. So if you decrease the temperature, you're pulling the heat out of the reaction. And the reaction's going to try and make more heat. But it can only make heat if it moves to the product side. So decreasing the temperature is going to shift this reaction to the product side. You're going to see the K value actually increase if you decrease the temperature. K increases as the temperature goes down because the reaction's trying to generate more heat. It's trying to warm itself up, all right? The concentration of CO2, the moles per liter, the product side CO2, is going to be increasing. And the pressure of CO2, the CO2 on the reactant side, will be decreasing. But notice here what I did. I thought about it as if you were like a human being. You get cold, you put a coat on. You get warm, you take the coat off, right? Well, this reaction's getting cold. It's going to try and make more heat, put a coat on. It's going to shift to the side with the heat, all right? It's going to move to the product side. If you increase the temperature, now the reaction's getting too warm. And if you go outside and you're warm, you'll probably take off a coat or whatever and stuff like that to cool yourself down. Well, reactions cool themselves down by using up the heat. So in this case, if you increase the temperature, the reaction's going to try and get away from the heat. It's going to move to the reactant side, a shift to the left, trying to use up the heat. Less heat would be its way of cooling down. So notice here that if you decrease the temperature, the reaction will shift to the product side. On the other hand, if you increase the temperature, the reaction will shift to the reactant side. It's trying to get away, or it's trying to get to the side of the thing you're changing. So we're changing the heat here. Decreasing the temperature is like removing heat. Increasing the temperature is like adding more heat. And the reaction's just trying to basically adjust to how you're changing it. If you can see this, you've got Le Chatelier's principle down. There is a Le Chatelier's principle guide, and I recommend you check it out for more information as well. Now, these reactions are changing the value of K, and we're going to see in a little bit, we're going to talk about Le Chatelier's principle for reactions that don't affect the value of K. Here's another example of this. Let's go back to the N2O4 equilibrium with NO2, and N2O4 is a colorless gas, while NO2 is a brown gas. Now this is an endothermic reaction, so you can think about it as heat being added, and this is the opposite of the soft drink example we saw just earlier. Anyway, if heat's being added, the delta H, the enthalpy, will be a positive number. So notice here the endothermic means positive delta H, and it also means heat's a reactant. In the last example, we had an exothermic reaction. You can think about it as heat being a product, and the delta H value would have been negative. Now, K here, products divided by reactants, NO2 squared divided by N2O4. Check out these numbers. As you go from 273 to 298, you are increasing the temperature, okay? That's what it means. 273 to 298, you're putting on a coat, all right? Or you're basically making the outside temperature better, I guess. Notice what happens for the equilibrium. You go from 0.00077 to 0.0059. We lost a zero going from 273 to 298. K is getting bigger. So we increased the temperature, we increased the heat, the reaction's trying to get away from it, it's becoming more product favored. So this is really cool. You can actually use this kind of information to make predictions as to how equilibria are going to shift. Endothermic reactions generally become more product favored as you heat them up, and the opposite, of course, if you cool them down.
In a sealed flask, we have a mixture of dinitrogen tetroxide, a colorless gas, with the brown gas, nitrogen dioxide. When we heat the flask, however, the dinitrogen tetroxide decomposes into nitrogen dioxide, creating more of the brown gas until equilibrium is reached for the higher temperature.
Notice how the flask became more brown, all right? That's because more NO2 had been formed at the warmer temperature than you had when the flask was submerged in ice, where it was more reactant favored. So literally more NO2, more brown, that's what's happening here. K is changing with temperature. The formation of ClF3 is exothermic, so again you can see heat is a product there. Cl2 plus 3F2 makes 2ClF3. So let's predict the effect of the equilibrium by raising the temperature, and there's three possibilities. No change, shift left, shift right. Okay, well we're raising the temperature, which means we're adding heat, and the reactions are basically going to try and get away from what you add. So if you're adding heat, the reaction's going to try and get away from the heat. It's going to try and make itself cool down. And notice here that it can do that by getting rid of the heat in the reaction by making more reactants. Well, shifting to the reactant side means a shift to the left. So in this reaction, we would say that if you heat it up, the reaction is going to have more reactants and fewer products. It's going to be a shift to the left. So notice that increasing the temperature on the endothermic reaction made more products. Here, increasing the temperature on this exothermic reaction made more reactants. If your system is made of gases, then you will see effects of volume and pressure as you change things around as well. Larger volume and less pressure will happen with more molecules. On the other hand, smaller volume, higher pressure will make the side with fewer molecules. So to make sense of this, let's go back here to the N2O4 NO2 example. Well, N2O4 is 1 mole, and that makes 2 moles of NO2, 2 NO2s. So more molecules would be the NO2 side, fewer molecules would be the N2O4 side. So if you start making higher pressure systems, adding like a neutral gas like helium or whatever, that's going to force the NO2s to make N2O4. Remember, every mole of gas is about 22.4 liters if it's ideal gas and standard temperature and pressure, et cetera, et cetera. So having 1 mole would take up a lot less volume than having 2 moles. And if you start pressurizing things, it's going to try and go to the smaller volume. That's kind of a neat thing. On the other hand, if you change your equilibrium to a smaller pressure or larger volume flask, i.e., if you went from a 1 liter to a 2 liter flask, for example, well, now all of a sudden there's a lot more room. So the reaction will adjust to the side with more molecules. So if you do that, go to a bigger volume, then you're going to end up with more NO2 than you would have N2O4. This only is affected by gases. It does not work for solutions. However, if you have gases, this can be really handy to make sense of the changes you see.
A sealed flask contains 3 molecules of nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure.
In the video, that was an example of lowering the volume. It's relatively easy to transfer a gas from one flask to the other. So we went from a big volume to a small volume that forced the NO2 molecules to come together to make N2O4. And again, if you reversed it, if you put that small volume gas into a large volume, then you'd predict that more individual NO2s would form at the expense of N2O4. So it's kind of neat to see how this stuff all works out. Here's the same reaction we looked at earlier, chlorine plus fluorine making ClF3. And it says here we're decreasing the volume, okay? So we're going from like 2 liters to 1 liter, something like that. What's going to affect? Well, notice on the reactant side here, we have 1 plus 3, we have 4 moles of gas. And on the product side, we have only 2 moles of gas. So if you decrease the volume, you're pushing them together tighter, they're going to go to the side with fewer molecules. So in this case, we'd say it's going to be a shift to the right. It's going to be a shift to the product side. Decreasing that volume pushes everything together. You're going to have a higher propensity then of the smaller molecule side than you would have the more molecule side. If you add a catalyst, there's really no change in the equilibrium constant itself. However, it does affect how fast you get to equilibrium. Catalysts will affect the rates of approach to equilibrium, so it makes it happen a lot faster. Catalysts themselves won't really change the equilibrium constant K, they just change how fast it is. You're more likely to not have to worry about K versus Q if you have a catalyst, hopefully, because it'll make the process that much faster. In the production of ammonia, NH3, all right, the equilibrium constant 3.5 times 10 to the 8th at room temperature. And this is actually a pretty important reaction. Ammonia is used for a lot of agricultural uses, so fertilizers, stuff like that. It's also used for a lot of military applications, so both yays and nays. But anyway, this almost always has a catalyst in it. A lot of times, apparently, which is iron with potassium hydroxide catalyst. Usually the identity of the catalyst is kind of a deep secret because if they let it out, then competitors could make it as well. But anyway, without it, this would take a lot longer. But with the catalyst, the reaction is happening a lot faster. We're going to look at several examples here, and let's use the Haber-Frisch as an example, where we have nitrogen and hydrogen making ammonia. And notice how the N2 and H2, there's a total of 4 moles on the reactant side, and on the product side, 2 moles of ammonia, 2 moles of product. So this weird YouTube thing on the bottom here. This isn't the cool YouTube with cat videos that I'm obsessed with. Also professionally, of course, for videos like this one. But anyway, in this water YouTube, the left side is bigger than the right side. All right, and that represents like 4 moles to 2 moles, that kind of thing. If you change concentrations, moles per liter, all right, by say adding N2 or subtracting NH3, you're not changing the value of K, but you are changing the position of the equilibrium. And this crazy YouTube thing actually works pretty well to describe it. Now, YouTube is basically a factor of, the volume and gravity and stuff like that. And we can talk about taking away or adding reactants or products as we go through it. And again, remember, on the left side, that would be like the reactants, and the right side would be products. And right now, you can see that line across the line, that would be the equilibrium position. And we'll talk about how changing, adding reactants, adding products, removing reactants, removing products will affect the relative amounts of reactants and products, even though the overall equilibrium has been maintained.
When we add water to the tank on the left, the water in the tank on the right moves up, and that on the left moves down. The water moves from left to right, so we say that equilibrium shifts to the right, as it would if we added more reactants to a reversible chemical system.
In this example, the water U-tube was totally at equilibrium, and we decided to add some reactant. So maybe we added N2, maybe we added H2, whatever, okay? But the important thing here is we added a lot of water. Well, the water is going to push down on that U-tube, and in the process, the product side, the right side, goes up, and the reactant side goes down a little bit. So adding a reactant makes more product, all right? The reaction's trying to get away from what you've added by making more products. It's trying to use up the excess reactant. So if you add a reactant, the system will shift to the product side. It'll be a shift to the right. And this happens all the time. If you add something by Le Chatelier's principle, the reaction will shift to the opposite side of what you added. And that'll be important too. So adding a reactant, the reaction moves to the right, more product is made. So back to this example, chlorine and fluorine making ClF3. What's going to happen if you add chlorine? Well, chlorine is a reactant. It's going to shift to the side opposite of what we added. So in this side, if you add chlorine, you should end up with more ClF3. That's going to be a shift to the product side. And this is exactly what we saw in the video. We added a reactant. The reaction shifted to the product side, shift to the right. Adding makes the reaction shift to the opposite side of what you add.
Removing water from the left tank causes water to move from the right tank to the left. Equilibrium shifts to the left, as it does in a reversible chemical system when we reduce the quantity of the reactants.
In this example, we removed a reactant, and you can see that as you removed a reactant, the water pushed itself over to the other side. This is what happens when you remove something. Removing a chemical from an equilibrium makes the equilibrium shift to the side you removed. So if we decided to remove N2 or decided to remove H2, a lot of the NH3 will break down and become H2 and N2 to fill it in. So removing a reactant, we have a shift to the reactant side, a shift to the left. If you remove something, the reaction shifts to the side you remove from. And that's kind of a neat thing. The equilibrium is still maintained, you're just having less product, more reactant to compensate for the reactant you removed. This reaction again. Predict the effect. Removing F2. Okay, well, we're removing a reactant. The reaction's going to shift to the side that we remove. It's going to shift to the reactant side. This is going to be a shift to the left. All right, so again, adding shifts to the opposite side. Removing shifts to the side you removed from.
Adding water to the right tank causes the water of the left tank to rise as water moves from the right tank to the left. Equilibrium in the system shifts to the left, as it would if we added product to a reversible reaction.
Remember how I said adding shifts to the opposite side? Works on the product side as well. So in this example, we're adding product water. The reaction moves to the left to try and compensate for it. If you add ammonia to a reaction, you're going to end up making more relative amounts of N2 and H2. So again, Le Chatelier's principle, you add something, reaction shifts to the opposite side of what you added. This would be a shift to the left. We added a product, it shifted to the reactant side. Same problem. I know you're getting sick of it. I am too, I guess. But anyway, here we're adding ClF3, adding a product. So adding something, the reaction shifts to the opposite side. That would be a shift to the reactant side. That's going to be a shift to the left. Adding something, it shifts to the opposite side. Removing something, it shifts to the side you removed from.
Removing water from the right tank lowers the water level of the left tank as water moves from left to right to regain an equilibrium. The equilibrium shifts to the right, as it would in a reversible chemical reaction if we subtracted product from the system.
This last one is probably the most common. Usually you want to make the product, and if you want the most product you can make, if you can remove the product while the reaction's in equilibrium, the reaction will, as this one happened, shift to the product side. Because again, you remove something, reaction shifts to the side you removed from. So removing product, the reaction will move to the product side. More reactants will be used up and more product. So if you can continuously remove product, the reaction will constantly try and make more and more and more and more product. You end up with more and more of what you're looking for. Kind of cool. So let's go back to the butane-isobutane equilibrium. We looked at this earlier. Isobutane was the 2-methylpropane, K value 2.50. It is product favored. We would expect to have more isobutane than butane. Let's say we have an equilibrium set of concentrations where the isobutane is 1.25 molar and the butane is 0.50 molar. Remember, 1.25 divided by 0.5 is 2.50, so that is an equilibrium set of conditions. But now we decide to add 1.50 molar butane, the reactant. So first of all, we're adding a reactant, okay? And it says when the system comes to equilibrium, what are the new concentrations? Well, we're adding a reactant, or adding something. The reaction's going to shift to the side, to the opposite side. So we would expect then the shift to be to the product side, i.e. more isobutane will form as we add more reactant butane. And that's kind of cool.
Butane and isobutane can interconvert to reach a dynamic equilibrium. The graph shows the equilibrium line. If we add butane to the system, the equilibrium is disturbed, and the butane reacts to form isobutane until the equilibrium is reestablished.
I like this graph. The red line is a slope of 2.5. And in some ways, an equilibrium constant is like a slope, all right? And so anytime you have an isobutane to butane mixture, which is 2.5, then you're going to be at equilibrium. So initially then, kind of down here in the bottom, that was a place where the equilibrium was. And if you look on the left, it's about 1.25, and you go straight down, it's 0.5. Well, all of a sudden now, we've added a whole bunch of butane. 1.5 plus 0.5, you end up then with a value over here that's about 2. That it's no longer at equilibrium. You're no longer at that slope of 2.5. So what's going to happen in an equilibrium system is the system will adjust to make more isobutane. You're going to end up with a higher value, again, where the isobutane to butane ratio is 2.5. So mathematically, this is kind of what happening. Below the 2.5, you can see that's where Q is less than K. And above the line right there is where you'd have Q greater than K, where you'd have too much product relative to reactant. So that's another way you can think about equilibrium if you want to. So what you can do is right away calculate Q once you've added the additional 1.50 molar butane. So again, Q and K have the same form. It's going to be iso on top and butane on the bottom. So iso is 1.25. The butane comes from two sources now, 0.50 plus 1.5. Q 0.625. Now Q is certainly less than the K of 2.5. This is not at equilibrium. Q wants to be like K. That's when the reaction is back in stasis, if you will. Q is going to have to become a bigger number. And if you're going to make a bigger number from a smaller number, there's two things you can do. You can make the numerator bigger, so you can make 1.25 a bigger part. On the other hand, you can also make the value of Q or K bigger by lowering the reactant side, lowering the denominator. So we're going to do two things here. We're going to make the top part bigger, the smaller part, the bottom part smaller. This is a shift to the right. We're making more products, more isobutane, having less reactants. So we're going to predict here that 1.25, that number is going to go up, and the 2 value, total 2.0 value for butane will go down once equilibrium is established. Let's set up our good old ice table here and see if we can figure out what's going on. We only have one reactant and one product. You can see here that initially we had 2 sources of butane for a total of 2.0, and the isobutane was only 1.25. Now, Q is getting bigger. Q has to become bigger. That means more product, less reactant. So we're going to have a positive X for the change of product and a negative for the reactant. So at equilibrium, 2 minus X, and at equilibrium, the isobutane, 1.25 plus X. Well, here's our X values at equilibrium. We know what the K value is, so let's throw it all together. 2.50 equals 1.25 plus X divided by 2.0 minus X. Now at this point, if your math haven't done it for a while, I'd like you to try and go from this part to an X value of 1.07. This is a good test of your math skills. I want to make sure you've got it. Yes, you can absolutely cheat if you have the solve button, but if you don't have the solve button, here's what you would do. 2.50 times, parentheses, 2 minus X equals 1.25 plus X. That's the first thing you want to do. You want to get the 2 minus X out of the denominator, and then you'll have X terms on both the left and the right. So you want to then multiply 2.50 times 2 and minus X. You would have 5 minus 2.5x equals 1.25 plus x. You then want to combine all of the x's together. You want to get x by itself, so you'll divide both sides by whatever's in front of the x. You should end up with 1.07. If you are not getting 1.07 for x here, then please reach out to me. Send me a little screenshot of what you're doing. From a camera phone is fine, and maybe I can see like how you're doing it and give you some hints for getting the right answer. None of this stuff is hard, and it's all stuff you've done before, but it's not something that most people anyway, do every day. But I want to make sure you can do it. So make sure you can go from the k expression to the x of 1.07. You don't need a quadratic or anything like that. Anyway, with a 1.07 number, then you can calculate the new value. So the butane was 0.93. That comes from 2 minus 1.07. The isobutane, 1.25 plus 1.07. That's 2.32. And again, because K was larger than 1, of 2.5, we would expect more product than reactant. We do see the isobutane is larger than the butane. That's good. Equilibrium has shifted to the right. It was at 1.25 and now it's 2.32. So adding a reactant made the products go up. Good to go. An overview of Le Chatelier's principle, I think, is kind of helpful. If you change the temperature, all right, you are changing the actual value of K, and you can change all different kinds of things. You can change pressure, volume, concentrations, anything you want. This is where we had the endothermic, exothermic discussions, and you can remember that adding heat is like adding heat to the reaction, so it's going to try and cool itself off. On the other hand, if you cool it down, that's like taking away heat, and it will try and adjust. If you use a catalyst, you don't change the value of K, but you don't usually then have to worry about waiting for the reaction to get to the equilibrium position. So you don't usually need Q versus K, stuff like that. That's not for sure, but that's at least more likely. Catalysts just make reactions get to equilibrium faster, and that's usually a good thing. On the other hand, if you add or take away reactants or products, you don't change the K. Like the equilibrium water position was the same, but it will adjust to the new position. And in a nutshell, this last one, if you add something, the reaction shifts to the opposite side. If you remove something, the reaction shifts to the side you remove from. That's kind of an overall view that works really well for Le Chatelier. It also works for temperature too. If you think about it as increasing the temperature is like adding heat, and decreasing the temperature is like removing heat. Okay, that's the end of chapter 13. I really appreciate you spending your time with me. If you're new to my world of teaching, at the end of these chapters, there's always a reference to a study guide and a concept guide. A study guide is a bulleted list of highlights from this chapter, and I do recommend you go through the bulleted list and just make sure you're kind of good to go with the ideas. Concept guides, which are in your companion and online, are worked examples from some of the concepts we've looked at in this chapter. So if you want to see more examples how to calculate K or how to use Le Chatelier's principle, I do recommend you check out the concept guides. Sometimes I'll have important handouts, and definitely for the first couple chapters, this types of equilibrium constants handout I think can be really helpful. We're going to look at lots of types of K. In this section, we looked at KC and KP, but there's lots of other ones. And later on, if you forget what a KP is, looking at that handout might be helpful. Now, I don't usually show them in these videos, but I will today. After this slide, there will be a list of important equations, which are kind of the important things, I think, kind of from this particular section. And then there are also some end of chapter problems. And on the one slide, I'll have the questions, and the next slide, I'll have the answers. And I do recommend that you know how to go from the questions to the answers. If you're not getting them, then obviously reach out to me, and I'm more than happy to help. Here are the important equations from this section. All right, these are the things that I think are kind of important. And again, every chapter will have different ones. And then after the important equations, here are the questions. And so here's 5 questions from this section, and there's all the information you need. And I would absolutely recommend trying these questions. And then here are the answers. And if you don't get the answers, then definitely let me know. I'm happy to help. Okay, again, I appreciate you spending your time with me. If you do have questions on any of this, reach out to me. Email is awesome. You can also reach out to the Learning Success Center /Avid Center, and they can help as well. Good luck with your studying, and have a wonderful day.